Our second example in multiple regression is going to display a curvilinear relationship between at least one of the x variables and the y variable. The scenario involves pro golfer earnings, where we had 21 pros that were tracked last year and their earnings were recorded. The two variables that appeared to be somewhat related to earnings were the number of events the golfers entered and the golfers' scores. Look at your graphs. There's just a little bit of slope evident with events, but there definitely seems to be a relationship between score and earnings. However, when we draw a straight line in there, the points don't fit that as well as a curve would. So let's see how we handle that. In the residual plot, we see another curve. And again, that tells us we misspecified the model if we tried to make it a linear model. Now let's look at what if we tried everything we possibly could with the two variables events and score. In this first equation, you see earnings equals beta sub naught, that's the y-intercept, plus some coefficient for events, plus a coefficient times score, plus a coefficient for events squared, plus a coefficient for score squared, and finally a coefficient times the interaction of events times score. So when you look at the variables, events and score are first order terms. Events squared and score squared are called quadratic or second order terms. Then events times score is known as an interaction term. It is also second order. So when I put all of these variables together, when every variable that's quantitative is squared and interacted, it's called a complete second order model. So a lot of times, if we don't have a lot of variables, we could start with a complete second order model, then reduce it down to only the good predictors using stepwise. We also would like to check the coefficient of determination. Suppose that in the first run of the complete second order model, R squared had been 0.9596 and R squared adjusted was 0.85. That's more than a 10% difference, and that's called artificially inflating R squared. We had 21 samples and 5 predictors in that first equation. So that is the cause of the artificially inflated R squared, because R squared will keep going up every time we enter a new predictor in the model, even if it's not a good predictor. So we should have had a sample size of 50 or 10 times the number of predictors to accommodate the size of a complete second order model here. When I let stepwise help pick out what to keep and what to throw out of the model, I discover when I click on Go that it checks only score and score squared. So events really didn't help predict anything in the model. So I'm going to rerun the model. And the very best predictor that comes in step 1 is score, then score squared, and that will reveal the best model with R squared of 0.9563. Here's our final model. You'll notice that it's gone into scientific notation due to the fact that the earnings were in the millions. We could avoid that by putting them in as, say, 4.5 million, 7.2 million, whatever the values had been for their original earnings. R squared is 95.62%. So 95.62% of the variation in earnings is explained by this model. And our residuals now display homoscedasticity, which is preferred. Looking at the prediction profiler, we can now predict a golfer's earnings based on their score. So if golfers made an average score of 70, their score squared would be 4,900. Approximately $3,202,239 could be earned. Then looking at the bracketed values under Prediction Profiler, we would interpret that as using 95% confidence. The mean earnings for golfers with scores of 70 will earn between $2,952,442 and $3,452,036. This concludes our example today. Keep working the problems that are in the book. Check them with the answers in the back of the chapter. And there's also copies of the PowerPoint shows that came with the book in the back of the entire book.